Hello, welcome to the presentation of my results of the second lab about the motion of a falling object. In this lab, I first observed a falling object and then created two different models and compared the observations with the predictions to evaluate these models. In my experiment, I dropped a piece of wood from a balcony. The piece of wood had a mass of 0.379 kilograms and a length of 37 centimeters, a width of 14.1 centimeters and a height of 1.9 centimeters. The total height of which the wood was dropped from was about 4.4 meters. To further analyze this motion, the tool tracker was used next. There, at first the right frames had to be specified. The falling occurs between frame 11 and frame 36, which equals exactly a time of 1 second. To specify the length with the calibration stick, I used a perpendicular with a length of 4 meters. Finally, the coordinate system was set to the center of the piece of wood in the first regarded frame, with a positive x-axis upwards and a positive y-axis to the right. By specifying the center of the piece of wood in each frame, the data of this movement can be obtained. To predict the motion of the piece of wood, a model was created. This model used Newton's second law, which states that the new velocity of an object after some time delta t depends on the ratio of the current net force on the object and its mass plus its current velocity. With this, a new position can be obtained. Then, a new velocity can be calculated, and so on. In this first model, the net force consisted only of the gravitational force. This leads to the following equation for the new velocity. As you can see, it is independent of the mass of the object because it cancels out. Now a few initial values and parameters are needed for the model. These include the start time, the initial position and velocity, the time step length, and the end time. This model was then implemented with Python. In the code, first the initial values and parameters are defined. Here the vector j hat is used to denote the direction of the gravitational force, which points in the negative y-axis. Then in the main loop of the program the net force is calculated by calculating the gravitational force on the object. With this, the new velocity and the position of the object are determined and saved into a file, and the time step is increased. This loop repeats for the length of the experiment. Now the program could be executed and the results could be compared with the observations. This graph now shows the model predictions and the observations of the experiment. The x-axis corresponds to the elapsed time and the y-axis to the position of the piece of the wood. The red line represents the model predictions and the blue dots the observations from the experiment. As you can see, the model predicts the data of the experiments fairly good in the beginning, but after half a second the difference gets bigger and bigger. In the end, the total difference is about half a meter between predictions and observation. This is because real-world effects like drag through air resistance are not incorporated into the model. As a consequence, the model had to be adapted. Besides gravity, the net force now also consisted of a drag force. The drag force was in the opposite direction of the velocity and had a magnitude b times the square of the magnitude of the velocity. This led to a new resulting model which was no longer independent of the mass of the object. This model needed the same initial values and parameters as the former model, plus a drag parameter b. This parameter was determined empirically, so that the final model prediction of the position matches with the correspondent observation. For the new model, the Python code had to be adapted slightly by setting the parameter b and calculating the drag force and adding it to the net force. Now the results of this model could also be compared with the observations. Now the results of the second model are also shown in this graph. As you can see, it is a big improvement compared to the first model. However, it is still not perfect, in the middle at, for example, 0.6 seconds. This could be because the camera might not have been perpendicular to the movement. Another problem is that the fall of the object was not synchronized with the camera. So the object does not necessarily start to move at t 0 seconds. If the timescale was longer, one also could observe that the second model predicts a terminal velocity. This happens when the magnitude of the velocity is high enough so that the drag force equals the gravitational force and the net force is 0. Finally, one could ask what would happen if the object was thrown downwards. In this case, the terminal velocity would also be the same, but it would be reached faster.